Assalamualaikum and good morning. So welcome back. I think we had sort of a unexpected break. So let me just make the presentation now. Okay, some delay. Sorry. Okay. You see my screen soon? Okay, are you seeing my screen? So again, I'm going to do this on the whiteboard. I'm still, despite the break, I'm still typing up the notes. Right, so let me just hope you can see the whiteboard. Let me just what we did call previous lecture. So what we did was to look at some examples of simple quantum systems. And this includes particle in a box. And we essentially write down your partition function. And we can derive things like free energy and then other physical quantities. Okay, so that was what we did, and also later on we need to differentiate between these simple cases with much more realistic cases. The system for particle in a box are referring to translational motion. Okay, so we shall see later on, hopefully we have time, we shall see later on for a much more realistic description, one needs to include other types of motion like rotational motion and vibrational motion. Before we do that, let's discuss on some other things like how to essentially calculate or find the relationship between what we see in the what you call the Boltzmann distribution thing with things that you already know about thermodynamics, which is heat and work. Okay. So this is a particular section of the book which talks about that. So let me bring this up. Okay. So so the idea here is one looks at so heat and work usually comes from some thermodynamics relationship that we had earlier on, which is related to say something like U equals to Q plus, oops, what is this? Q plus some work done kind of thing. Okay, so this the first law thing, usually in terms of differentials. Okay, so I have that. Okay, first law. So we would like to relate this with something that we already done using Boltzmann distribution and also the partition function. So how to do this is to relate it with the average internal energy. Remember, in a canonical ensemble, each system can actually change energy. So one can sort of look at the average of the internal energy of each particular system. So just write that down. Average internal energy, which is can be given by this notation. U bar is the average, so can be given by the sum of the probability of each energy state or energy levels times the probability. So this is just the normal formula for mean value. So you have the probability of the energy level here times the energy, and then sum it over, then you get the average energy. Okay, and what is this probability? Is coming from the Boltzmann distribution thing. So pi equals to exponential minus ei on, make that a bit clear, ei over kbt. Oh, not forgotten, over the partition function. So the partition function, as we know, in the first instance, is like a normalization constant. So that you need that. So if one takes, so remember, we want to get back to this point of having the, okay. So what do? We take the differential of this average internal energy. So in this particular case, so take differentials so there one so let me just write it down first, du bar. So there are two quantities over here, so you take the differential of each, so that means you have two different terms. So here you take the differential of the probabilities, and then leave out the energy levels, and then another term which is keeping the probabilities, and then take the differential of the energy levels. Okay. Now the idea is now to compare this with the earlier expression that I've already done or mentioned above. You have, this is related to some heat input into the system plus the work done. Okay, and these are normally what we call inexact differential. Okay, so how do we make that comparison between the two? So we need to compare this. Well, one of the things one can try to do is take special cases. Okay. So one of the things that one can actually do is to make all external parameters, for example here, to be held constant. And remember that your energy levels depend on these parameters. Will also be constant. Okay, so this is a special case where you have all those parameters constant, and then your energy levels are also constant with respect to this infinitesimal change that we are trying to do. So in other words, in this particular case, what do you have? you have your DI equals to 0. Okay. So in other words, the condition that we have over here, this term will be 0. Okay. So and if you have all the external parameters to be held constant, so there will be no work done, because usually when we talk about work, you change some parameter, for example the volume, okay, and then you see how the response to that change in volume, which gives you the mechanical work, usually in terms of PDV. Okay, so in this particular case, then what we have, we can make the identification over here when external parameters. Okay, let me just write that down. No work done here, as external parameters are constant, held constant. So one could now essentially say, okay, this is 0, this is 0, so the one that we can identify is this term with that term. Okay, so now let me just write that down. So can identify the Q equals the sum of dpi ei. Okay, and in a way this makes sense, because if you want to have a change in the internal energy, okay, you want to have a change in the internal energy, and your parameters are held constant, the only way that the energy can be increased or decreased, for that matter, is through inputting some heat energy or not extracting it. Okay, so there one has that term to be identified. That means the other term which is going to be the work, so work done is now identified as sum over pi d. Okay. Now the fact that this is actually done for how should I say, the changes here, okay, the changes made over here, let me just put it in red. Changes are infinitesimal. Okay. So in that way, one could make that identification. Okay, but when your changes are not infinitesimal, can't separate out or can make the identification. Okay. So let's proceed with some example. So consider the case. So here's an example. Let's consider gas atoms in a box of volume V equals to L cube, which have done in the context of the three-dimensional box that we had earlier. So your single particle energy levels is given by, let me just write that down first, h bar squared pi squared 2ml square, and then you have this addition of squares of your three different quantum numbers, which represent the modes of your standing wave in the box. Okay, but now what we want to do is to rewrite this in terms of this volume as an external parameter instead of your L. Okay, so let's do that. So you get your h bar squared pi squared over 2m, and then this should be v 2/3. Oh, it's not something about. Okay, and then you have the same sum of the quantum numbers. So now your energy levels are now dependent on this parameter. Okay. So let's push that up. So now one could actually write down the change in energy levels by changing the volume. And for our purpose, let's say we are shrinking it. Okay, so what we do in this particular case, you take the derivative, and to say that shrinking, one should have a minus sign. I'm going to put a minus sign on the other side. So that gives us, well, okay, I mean, it's already in the denominator. So you have that minus 2/3 there times that number to m, and then we 5/3, and then the quantum numbers. Which you can rewrite in a much more simplified form using the terms epsilon I there as 2 epsilon I over 3. So and this is for each single particle energy level. So for the case of total energy, so total energy will be given by the sum epsilon I. So in other words, if you take the derivative there, this will be just giving you the similar what you call expression. Okay, so that is more or less looking at the terms, let me go back, where you change essentially your energy levels. So that will be related to the work done. Write that. So work done in that particular case is given by minus P dV, which is now equated with our PI DEI, which you can now write as PI partial EI partial V dV, and that can be written as minus 2 over 3 over V sum PI EI dV, which you can write that since PI EI is going to be sum over, okay, and that gives you your average internal energy. So comparing this with that, okay, then you find that, okay, I can now get this sort of equation of state in some sense, which we have seen before. PV equals to 2U bar over 3. So one can do that kind of analysis with respect to this using the differentials to find out the heat and work. There are other types of work, for example, other types of work, for example, Siemens Effect, where essentially if you done some form of atomic physics or modern physics, this is essentially the coupling of magnetic field okay, with energy levels. And then your Stark effect is another one. So here, for example, one can think of your magnetic field to be your external parameter, and then you can get your magnetic work, which is actually explained in the book, which I'm not going to go through, but it has the similar kind of analysis. Okay. Stark effect is essentially energy shift due to the electric field. So again, over here, one considers the electric field. Okay, the electric field here as external parameter, just like your magnetic field here as an external parameter, and also compared to in the case of the one that we done above, where your external parameter essentially is your volume. Okay, so I think I want to skip the rest. You can read on magnetic work inside the book, and perhaps later on when I type out the notes. Okay. So now for the rest of the lectures, I will start to talk about how to generalize the sort of canonical ensemble, not only to consider translational motion, but other kinds of motion. Okay. So let me clear the whiteboard. Okay, so here is now you want to consider, say, rotational motion, and for this we need so for rotational motion need the, how should I say, the physical particle to have more structures. So the simplest case will be a diatomic molecule. So diatomic molecule where you have consists of two different atoms normally separated by some distance, separated by distance d, for example. Okay. So what can happen is that now, given that this kind of cartoon picture of the molecule here, so you have this distance between the two. Once one can start to imagine that this is going to be rotating about some central mass of between these two molecules. Okay, so really what one needs to think about is how energy states depend on this rotational motion. Relate energy states with rotational motion, usually given by your characterized by your angular momentum. I think I remember that you have mentioned to me before that you have done quantum mechanics, so we're going to just do a little bit of revision here. So when you do orbital angular momentum in quantum mechanics, in QM, essentially your states are characterized by quantum number, which is denoted by L. Okay, I think this is called angular quantum number. Sorry, angular momentum quantum number. The states themselves usually denoted Lm. I'm not sure whether you have seen this kind of notation before. So your L is your angular momentum quantum number, and your M is what we call the magnetic quantum number. Okay, so that to differentiate with states of different M, usually one needs a magnetic field, for example. So so how do you get the energy states by doing how should I say, if you do classical mechanics, okay, you're going to do jumping back and forth, your rotational energy can be given by L squared over 2I, where I here is your moment of inertia. L here is the magnitude of your angular momentum. So this is in classical mechanics, okay? If you have not seen this, you may want to look it up. But the point here in quantum mechanics, L squared has quantum number, oh, sorry, I should not say quantum number there, has eigenvalues, L plus 1 H, oops, why is it doing that? L plus 1 H bar squared. I believe you have seen this expression before. Maybe I should check with you. You have gone through angular momenta in quantum mechanics, right? Somebody?
Yes, doctor.
Okay, great. So you should be able to understand where this comes from. Okay, so now essentially I'm going to replace that L squared, okay, by your eigenvalues. Okay, so in other words, what we have, so one has rotational energy levels, which I'm going to denote by epsilon L here because it depends on this L. So will be given by h bar squared L plus 1 over 2I. And what is this I? I comes from the ordinary moment of inertia. In this particular case, it's going to be written as mu d squared, where mu is your reduced mass. Okay, remember that you can have two different masses for the diatomic molecule. Okay, so you have two different mass over here, m1, m2. So mu will have to be m1, m2 divided by m1 plus m2. Okay. Oops, what am I doing? Okay. And your usually one has an axis, rotational axis. Is through the center of mass. Okay. So what else do we know about this so-called eigenvalues? You have to remember when those eigenvalues will still have this other quantum number that comes here. Okay, so giving you the same same angular momenta but different components of your say Z component in this particular case usually. So in that particular case, you have different states. So have different LM states corresponding to each L. Okay? And the M values, if you have done quantum mechanics, you should be able to see this, have seen this before. It goes from minus L to L, and there are 2L plus 1 different values of M. So there is a degeneracy here. Okay? So you get energy degeneracy, which is written as GL, which is given by 2L, the 2L plus 1 different M states. Okay. So I hope you have, okay, let me just sort of give you the degeneracy level. For example, for the case of the zero angular momentum, you have only one. So for L equals to 1, there will be 3. For L equals to 2, there will be 5. Okay. So this will go into your partition function later on. Okay. So what is a partition function for these rotational states? So remember at some point I think I've mentioned this. So I have the GI exponential minus epsilon I on KBT. Okay. So this we have done before. So in this particular case, will be sum or L equals to 0 to infinity of 2L plus 1 exponential of h minus h bar squared L plus 1 over 2I KBT. Okay. So once you have this partition function, then one could actually calculate, so once you have partition function, you can calculate free energy, then from free energy, you can calculate entropy, and from entropy, you can calculate heat capacity. Okay. But let's look at some simpler cases or extreme cases first. So there are two extreme cases that you can think of. One is, okay, so there are two cases really. So the first case is one looks at a large h bar squared on I KBT. Okay. So when you have this to be large, when it goes into here I mean your L could be ranging from L equals 0 to infinity, but since h bar squared on I KBT is large, when undergo the exponentiation here with a minus sign, so here then you have your sum involve small exponents. Okay. So when you have small exponents, one could sort of truncate your partition function. So truncate, because you're adding smaller and smaller exponents. So truncate partition function to involve only a few terms. Okay, so in this case, I can take Z equals to 1 coming from L equals 0. So here is L equals 0 here. And then L equals to 1 will be giving you 3. Okay, the 3 is the degeneracy of L equals to 1. Exponential minus h bar squared. Remember, it's I plus 1. So that will be 2. And 2 divided by 2I kBT. That gives you I kBT. And if you want, you can add higher order terms, but we're going to just stick to L equals 0 and L equals to 1. So with this, call partition function, if you look at what log z is, because log z will appear in free energy, I can just simply write it down over here. Oops, too far away. Log 1 plus 3e minus h bar squared I kBT, which I'm going to stop at that particular term. And remember that this is small, then you remember your power series for log 1 plus x, where x is small, it's going to be equals to x minus x squared on 2 plus x cubed on 3 minus x to the 4th and so on and so forth. Okay, so I can always truncate it to the first term here. So I will get, for example, here to be approximated by 3e minus h bar squared on I kBT. So now we can, once you have that log z, you know your free energy is given by F equals to minus kBT log z. Okay, and that will just simply give you minus 3 kBT exponential minus h bar squared I kBT. Okay, so one could further calculate. Okay, so from here one can further calculate your entropy. For example, your entropy is given by partial F partial T, and from your entropy one can actually calculate your heat capacity. Oops, what is that? Okay, so one could do this. I've done only partial. I think probably can be done as an exercise here. So right. So remember, we only have looked at the case where the extreme case where this is actually large. The other extreme case is to consider it to be very small. Okay, so the case your h bar squared on I kBT to be small. And remember, when you do this, we need the partition function just now. So this is going to be sort of small. Okay, so you have all this sum involving this small number on in the exponent. So one could actually replace the sum in Z by an integral. Okay, so let's do that. So what do we need in this particular case is perhaps remember that you need the sum over L over here. So I need to replace this by some integral over L. But let's make this easier for us because remember that you have your L plus 1 thing. Okay, so I'm going to call this Y. Okay, and then instead of integrating over L, which is involving this quadratic term, I'm going to integrate over Y. So this will be 2L plus 1. Yeah. So plug this thing into your partition. Now with the integral rather than the sum, so you have Z equals to integral from 0 to infinity of exponential minus h bar squared y on 2I kbt dy, and you can work this thing out to be equals to 2I kbt on h bar squared. Let me try to finish this. Okay, so then we can, for the next lecture, we can go straight into vibrational energy states. So free energy is given by F equals to minus kBT log Z. So you have log of 2I kBT on h bar squared. And then your entropy is given by minus the F dt and remember in your free energy there are two T's appearing there, so you do the differentiation for each, so you should be getting this. The log, first differentiate that, so I get the log of 2I kBT on h bar squared, and then I have to differentiate this, keeping that constant, and then the factors coming out, and that will cancel off with the terms, and that gives you 1. Okay. And finally, here one can calculate your heat capacity. So heat capacity is given by d s dt. Again, I hope you can actually do this yourself. This is giving you kb. So if you work out for the case of the other extreme case, there will be some dependence, and if you try to plot this against temperature, let me go to the book. So you have this kind of picture. Let me take a snapshot of that. Okay. And place it here. So you have this. Here is in units of kb. So you can see at high temperatures, this sort of levels off to 1. Okay. And for the low temperatures, we did do the calculation just now, but you can actually, no, it's a bit more complicated there. So you probably need a little bit more work on the derivatives, so you get this sort of almost exponential kind of thing. Okay, so let me just finish off with another thing. There's a thing that they define as following. So one could actually, let me pull this up. Oops, that I want to move the whole thing up. So one can actually write your h bar squared on 2i to be equals to h bar cp. Your c is speed of light, and then if you do dimensional analysis, your b here has the dimension of 1 over L, and this gives you the essentially your rotational energy dimensions here. So, and I can, so this is an dimension of energy, so I can rewrite this in terms of the temperature, kb theta r. So this has the dimension of temperature now. And what is this temperature? It gives you the demarcation between the low, I should say, the low part of this curve with the higher part of this curve. Okay, demarcation of the, how should I say, the energy limits or temperature limits. Stroke temperature. Okay. So that more or less one could actually try to see where this, so there is this change in behavior. One could actually find that out for each diatomic molecule, and they have given that in this place in the next, see the next, yeah, this one, this table over here. So let's just take another snapshot of that. Paste it here. So here are some few cases of diatomic molecule here. So, and then they find out what this theta r is going to be. Okay. So I think that's all for today. We'll go into the vibrational energy states in the next lecture. So let me go to take your attendance. Sorry, where am I? Okay. So attendance. By the way, I'm a bit all confused now. What week are we in now? Because there are changes to the lecture schedule. Everyone knows? So when do you want to have your first test? A second test, sorry. Next week? Okay, if it's next week, then I will have to put out your second assignment sometime soon. Okay, so if it's next week, it will be on the Thursday. Okay. All right. So I think that's all for today. Thank you. So I need to stop now. Okay. Thank you, everyone.